Let's look again at our RNN. So this is at time step 1, time step 2, all the way to time step n, where n is our sequence length. As always, we have h sub 0 coming in, h sub 1, h sub n minus 1, and we have x1 coming in, y hat 1 coming out, y hat 2 coming out, x2 coming in. In the traditional backpropagation through time, we're going to go ahead and take our entire sequence length and we're going to run all the way forward in steps. So we're going to work in steps forward, and then we're going to do in steps of backpropagation. So we go in steps back. The problem is, if n gets very large, then we have a couple potential issues. So one problem is the concern about vanishing gradients. If we take the path through all these h sub n's, then we can have either vanishing or exploding gradient as we get early in the path, especially if it's long. The second, more important problem is it can be expensive to calculate this backpropagation. Actually expensive in terms of space, because we need, in order to do the backpropagation, to save the activations at every time step. And so if h is large, that can be a lot of space. This is all still stored on the GPU. And so we just may physically run out of space if n is extremely large. Or it may very limit our batch size. Because if you consider, right, we've actually got a batch of x's coming in, all of sequence length n. So for that reason, truncated backpropagation through time comes in. So truncated backpropagation through time defines two constants, k1 and k2. And they're both between 1 and n, where n is our sequence length. So we have backpropagation through time of n comma n says this is the number of forward time steps and this is the number of backward time steps. So if we go forward n time steps and backward n time steps, that is just equivalent to traditional backpropagation through time. Let's look at another possibility. If we have something like backpropagation through time of 1 comma n, what would that say? That would say we're going to move 1 time step forward, and then we're going to move up to n back. We're going to just move 1 back to begin with. Then we're going to move a second time step forward, and 2 time steps back, and a third time step forward, and 3 time steps back, all the way until at the end we're doing the nth time step forward and n time steps back. So if we look at this approach, we are doing cumulatively n forward time steps. So that's just the same as in our traditional BPTT. But we're actually doing 1 backward time step, 2 backward time steps, 3 backward time steps, all the way to n backward time steps, which is order n squared backward time steps. The advantage of this approach is we're doing a lot of updating of these early gradients. So in the early time steps, we're updating the weight matrices and in some sense overemphasizing those early time steps because we're updating those weights based on the early inputs more than we are later. Another approach that we can use is k comma k. So in this case, we'll go k time steps forward and then k time steps back. And then another k time steps forward, k time steps back, another k time steps forward, k time steps back, until perhaps at the end we do a smaller number so that we get the last few time steps if n is not a multiple of k. This works pretty well. So notice we're limiting the amount of backpropagation we have to do. Here, we're not limiting. We still have to go backpropagation n, just like we did here. So we still have to save all those activations in memory. Here, we only have to save k activations in memory. So that can allow us to have perhaps a larger batch size. One thing to note here, though, is we have this seam here. That is, we're not actually propagating gradient, propagating error back from time step, let's say k plus 2, to time step k minus 2. So we'd stop backpropagating here. An alternate would be something like backpropagation k to k. So in this case, we'd go k forward and then up to 2k back. K forward, 2k back. K forward, 2k back, and so on. So we can see here that we actually are overlapping our backpropagation across this seam. So we never have some particular elements, time steps, over which we're not backpropagating. If we look at PyTorch, PyTorch doesn't explicitly support 1n or k2k. In fact, all it really supports is nn and kk. So that is, k1 has to equal k2. It's perhaps our best description of it. So if you wanted to do k2k or 1n, you would need to implement that on your own. Doing the NN case is pretty straightforward. You would just go ahead and feed into the RNN each of your x1s, x2, all the way to xn. It would use the h0 as a default of zeros, right? So this would be 0 to be initialized to, and then we just go through, no, anything happens. How does KK work, though? Well, what you actually do is you're going to take your input and you're going to chop it into segments. So you're going to chop up your input that may be 300 long and chop it into 3 100 byte segments. Is it the same, though, to do a single calculation to n as it is to do 3 calculations, each with n over 3? Right? So here, let's say this is, here we've got h0 coming in, and that's zeros. Here we'd also have h0 coming in, and that's zeros. So we'd go from h0, and then in this case, we've got sort of an hk, and that goes into hk plus 1, and so on. What happens here, though? We would have an h sub k coming out, but then we'd start a new RNN. We'd feed in an h0 here. We'd have an h1 all the way to an hk. Here again, we'd have an h1 all the way to an hk, because basically what we're doing is we're running this, but instead of running it n times, we're only running it k times. The problem is that we don't want zeros to be coming in when we run the second run of the RNN, because that would mean we'd lost all our history. As far as the RNN was concerned, this was the beginning of a sequence, and we don't want the RNN to treat this as the beginning of a sequence. We wanted to treat it as still having the history that we went through the first k inputs. And so what we're going to do is actually take the output of h sub k and feed the output of h sub k into here. So we have an opportunity when we run an RNN to get not only the y-hats, we actually also can get out the final activation layer. And the reason we get that final activation layer is because often we want to feed that in to the next element in the sequence in doing this truncated backpropagation through time. So we're going to feed an h sub k in here. As far as this run of the RNN is concerned, it's got k elements in it, but it just so happens that the first history coming in is h sub k. That is, it incorporates everything about the first k inputs. And now as we get to the k plus first input, it's interpreting it with respect to all of this history. So the upshot of this really is that RNNs and the API for RNNs take in an h sub 0 explicitly. So if you don't provide one, it'll be set to 0. But if you do provide one, it will be used. And the output includes an h sub n. So you can actually retrieve what the output was as the final layer. And that's useful for a couple reasons. One, so you can feed in again. And then the second reason is so that you might want to just summarize kind of what has happened. What have we learned about this input? And that's captured in our h sub n. Let's look at the sizes of some of these tensors. Okay. So we have got a sequence of length n coming in. So this is the first instance, and this is all the way to the batch size. The way this is done in PyTorch is that we will normally have our input is going to be a tensor of shape n times batch size times, we'll call it the number of inputs, right? However many elements are in each x. Often can be one, sometimes can be more than one. Again, if you have three sensor readings, then you're going to have 3 values at every time step. So the input normally has the sequence length first, then the batch size, then however many inputs we have. Let's look at WXH. So WXH is of what form? That's going to be, so we know it's going to be the number of events as the first dimension, and then the second dimension is going to be some, let's just call it L. WHH, so WXH is going to be number of inputs times L. WHH must be something of the form L by L, and WHY is going to be L, or by number of outputs. Let's just see if this makes sense. Right? We know when we're computing h sub I, it's equal g of h times h sub I minus 1 times WHH plus x sub I times WXH plus b sub h. So we know h sub I minus 1 we're saying is an L by L. So, sorry, h sub I minus 1, we haven't actually said what the size of h sub I minus 1 is. We know xi times WXH is going to be, so let's look, what is x sub I? X sub I is going to be one of these. So it's going to be batch size times number of inputs. So this one, batch size by number of inputs. This one is number of inputs times L. So the total is going to be batch size times L. That means the output of this one is going to be batch size times L. So this means, well, first off, if this is batch size times L, this whole thing better also be batch size by L. And this is going to be 1 by L, and will be broadcast into here. And this one is going to be 1 by L, and will be broadcast under the batch size by L. We know that the activation function is going to keep the batch size by L, so therefore that tells us that h sub I is of the form batch size by L. And let's just make sure we're doing batch size by L, which is h sub I minus 1, multiplied by something of the form L by L, so that'll again give us a batch size by L. Batch size by L, L by L. So this all works out. If WHY is L by the number of outputs, then that says that any given y hat sub I is going to be of the form batch size by number of outputs. So we have the batch size again because we're always running through not just one sequence of x's, but a batch of sequence of x's. So if this is the input, right, n by batch size by the number of inputs, the total output, right, so this is the total input, we have a batch of x of 1s for all the different instances, and then we have a whole sequence of those, so we get the entire thing. Our total output is going to be, again, n by batch size by number of outputs. And because we've got all these ny hats, batch size, because we've got outputs for every single one of the different inputs, and then times number of outputs, because our y hats might be something other than output of one value. Right? Maybe this is a softmax over a variety of different values, for example. So we have the input, we have the output. We should also look at the output h, because what we get are the output y hats, and we also get the output h, right? So that we can feed it in to our next sequence if we're doing a KK truncated backpropagation. So our output h is going to be, don't have the sequence length, right? Because there's just one output, but it's of size, batch size, by L. And what is L? L is just our hidden size. So we just decide how big we want this to be. If L was 1, that would say H is just containing for each separate input, right? For each separate input in the batch, each instance in the batch, it just contains one number. So we're trying to keep track with one floating point number of all the history we've seen. That seems very limited, so we might increase H, and that increases the power. So we might increase the hidden size, and that'll increase this power. So our power is dependent on how many of these floating point numbers we're going to be maintaining. So as you can imagine, if we have 1,000 floating point numbers, we have a lot more memory we can keep track of what has happened than if we have one. But on the other hand, all of our matrices are going to be larger, because those are dependent on L, so we have more parameters, so it's going to be harder to train. We'll need more data. One note is, as you are doing these calculations, right, in PyTorch, each of these h sub i's is going to require a gradient. Because we've said that we require gradients for each of our weight matrices and our biases that exist as well. And so therefore, any calculations that occur based on these weight matrices also require gradients. So that means each of the h1, h2, all the way to hn is going to require a gradient. If we feed in the output of this h into another RNN, or another instance of the RNN, then depending on whether hn requires gradients or not, is going to depend on whether we're keeping all these activations. So if we want to do KK propagation, backpropagation through time, then we are going to want to detach this hn before we feed it in to the next instance of the RNN. If, on the other hand, we want to do something like K2K, where we are backtracking, then we would not want to detach this, because we would want our backpropagation to be not only the next iteration of the RNN, but also feedback through here too. So we'd want to go through the last two iterations of it. So we would have to be controlling basically whether we do this detaching or not. In FastAI, when you are using RNNs, in particular when you're using them for text, what happens is it actually will do this breaking apart into sequences. So it'll do this truncated backpropagation through time. So you specify what you want K to be. And I call that the sequence length. So let's say you have a bunch of reviews. So we've got some Yelp reviews, and we have got, I'm going to just show 3 Yelp reviews. Okay, so I really liked this shop because it was clean. The plumber did a good job. Hope to go back again next month. And so what's going to happen then is FastAI is going to arrange these into batches and into sequences. And it's going to arrange them into batches just like this. So these are batches. And they're different reviews, and that makes sense. But it's also going to break them up into sequences. And you actually get to specify when you are creating your data loader the sequence length you want. So let's look at a really short sequence length. Let's look and say we had a sequence length of 3. So it's going to break it apart here, and here, and here. And so what we get into any one instance of the RNN is going to be n times batch size times number of inputs. That is, we would feed in this case, our sequence length is 3, our batch size is 3, and the number of inputs to each one is 1, right? It would just be the word index. For the first sequence, it's going to go ahead and have zeros as the incoming h, 0. And then for this one, it's going to use the outgoing h of here to be the ingoing h of here. And then similarly, it's going to use the outgoing h of here to the ingoing h of the next sequence. And then it'll eventually, and then it'll be done. And then it'll work on a new set of batches. So we actually go through this way 3 times. They're going to run through the RNN. Here, and then here, and then here. And saving the output of one to the input of the next, output of one to the input of the next. So that is what FastAI is going to do. It's going to do some other things too. So notice that we're actually missing some words here. So it's going to put in padding, pad, 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 to ensure that they all end up the same length. So padding is just going to be a special index in our dictionary that indicates it's not a real word. The other thing that FastAI does is if you have 1,000 reviews, some of them might be quite short and some of them might be very long. It would be kind of a waste to put together longs and shorts in the same batch because the short ones are just going to get a huge amount of padding. So it'd be best to put the shorts together and the longs together. So we have long ones and we have some short ones. The long ones, we may need to call the RNN multiple times, right, with a sequence length of 3 in order to get to the actual width here. So if we looked at this case, we might have to do a bunch of different runs, each with our given sequence length. Whereas here, we might be able to get away with just 2, for example. So FastAI will sort your instances by length and put together the longer ones and put together the shorter ones. Okay? It does an approximate sorting as opposed to an absolute sorting because of the fact that from epoch to epoch, we want our batches to be different. We don't want to have exactly the same inputs in the same batch because we like the regularization that is provided by having different mini-batch contents on each epoch. And so it does an approximate sorting so that we don't have it completely just longest instance all the way down to shortest instance and then grab batches. Instead, it's roughly sorted so that there's not too much difference from each input. But when we do this sorting at the beginning of each epoch, we may get slightly different contents of each batch. So that's one thing it does. And the second thing it does is we talked about the fact that we have this hard link from k to k plus 1, and so we don't have any gradient going back across here. So what it actually does is adjusts the sequence size from batch to batch a little bit. So it might be 3 this first epoch, and then it might make it 2 the second epoch, and 4 the next epoch. So whatever sequence size you ask for, it'll do, plus or minus that. And it'll change that from epoch to epoch. So we have some different learning that's happened, because otherwise we're never going to have any gradient passing back from this second run across to this first sequence length. So from our second sequence length across to the first sequence length. So that's what FastAI does to try and get the most out of our working with an RNN.